In this video we're going to look at a thermal physics question. Pause the video now and try all parts of this question. Part AI says calculate the number of helium particles in the balloon. So we've been given the temperature, the pressure and the volume of the gas. So the first thing that usually comes into my mind is PV equals nRT, which is the ideal gas equation. Now we can't use this one. Why? Because this is the number of moles and we're being asked for the number of particles. So if you try and use this equation, you'll get the wrong answer. So you need to use the per particle version of the same equation. So PV equals big N KT, where this is the number of particles and K is the Boltzmann constant, which is given in the question but would also be given on the formula sheet. So now this is pretty simple. PV over KT equals the number of particles. So pressure 1.1 times 10 to the 5 times by volume 4.5 times 10 to the minus 3 over K times by our temperature, and temperature is obviously in Kelvin, so we need to add in 273. You could do that as a separate step, or you could just do it in the equation. That is equally clear. Let's quickly work out what this is. That gives us 1.6 times 10 to the 23. And if you don't get a very high number here, you're wrong, or you're probably wrong because it's the number of particles. Okay, II, calculate the mass of helium gas in a balloon, and they've given us a big clue here with these two constants. So we've got the number of particles, and that is equal to the number of moles times by Avogadro's constant. So if we use this equation, we can work out the number of moles, and then if we know the number of moles times by the molar mass, we get the total mass. So it's important to be very clear in your mind about exactly what this means. I would caution against just blindly remembering these formulas. They're not hard to figure out, and actually if you can figure them out, you're actually going to understand these questions a lot better. So let's firstly work out the number of moles, which is 1.6 times 10 to the 23 particles divided by the number of particles in 1 mole. So that gives us 0.27 moles, and then 0.27 moles times by the mass per mole gives us the mass, and you can see here as well the units. Okay, so I'm not always writing the units in, just to save a bit of time, but actually if you write the units in, it really helps. And if you're ever unsure, sometimes a lot of people get confused with this. If you write out the units, you can find out very clearly if you're actually working out the mass or you're working out something else like the inverse of the mass. So 0.27 times by 4 times 10 to the minus 3 gives us 1.1 times 10 to the minus 3 kilograms. Part B, explain how the motion of helium particles stops the balloon from collapsing. So this is a very standard question. There's basically 3 things they're always looking for in these questions. So firstly, the helium exerts or causes a pressure on the balloon. Okay, pressure is force divided by area. Alright, always useful to just quote the definition. the particles collide with the sides of the balloon. And importantly, you can't just write collide or collisions. You need to write with the sides of the container, with the sides of the balloon, because that's what they're exerting a pressure on. They're exerting a pressure on the side. If you just write collides, or the particles collide with each other, they're doing this, and this is not causing the balloon to stay inflated. It's only when the particles hit the outside that the balloon stays inflated. So particles collide with the sides of the balloon and change direction. This causes a force because force is rate of change of momentum, which is Newton's second law, which in formula terms is this, but you should always write it in words. That is obviously mv minus mu. So the three things: we've got a pressure is force over area. How is this force created? This force is created by particles colliding with the sides of the balloon, and the force is rate of change of momentum. Okay, part C. We've got a second identical balloon filled with hydrogen gas, and we want the pressure of this hydrogen gas. So the first thing that comes into mind is, can we just use this same equation that we used over here and work out the pressure? Well, we can't do this directly because we don't know this. Well, we don't know how many particles there are, but we can work it out. So the gas in each balloon has the same density, volume and pressure. So same temperature and volume is handy, because then we can just use the same variables in this equation. The same density, this is important. So now we can say that density times volume is the mass of hydrogen. So let's work out the mass of hydrogen. We can't do this directly because we don't actually know what the density is, but we can do another step. We know it's the same density as the helium, so we can work out the density of the helium, and that's going to equal to the mass of the helium divided by the volume, which is 4.5 times 10 to the minus 3. Which gives us 0.24 kilograms per meter cubed. So now we can use this value here to work out the mass of hydrogen, because that's going to be 0.24 times by the volume, which is 4.5 times 10 to the minus 3. So the mass of hydrogen is 1.1 times 10 to the minus 3 kilograms. So this was a largely pointless step, wasn't it? Because actually, if it's got the same density and the same volume, it must also have the same total mass. So this was a largely pointless step, which I should have realised. So we know what the mass of hydrogen is. So now what we can do is basically work backwards in what we did in this stage here. So we can do the mass of hydrogen divided by the molar mass, and that will give us the number of moles. So 1.1 times 10 to the minus 3 divided by 2 times 10 to the minus 3, this gives us the number of moles. So I don't need to put in the times 10 to the minus 3s because they cancel. So that's 0.55 moles. And then I can do 0.55 moles times by Avogadro's number, 6.0 times 10 to the 23 particles per mole to work out the number of particles. So we've got a number of particles greater than this, which is what we would expect because the molar mass is less. In fact, you might now have spotted there's obviously a quicker way to do this. If we know that the molar mass of hydrogen is half that of helium and it's got the same density and volume, it must have double the number of particles, and actually this is double that when you take into account the rounding that's going on. So actually all of this really was a waste of time if we'd spotted that. Anyway, we've got the number of particles now, so now we can say that PV is nKT, so the pressure is nKT over the volume, which is this answer times by Boltzmann's constant times by our temperature divided by our volume, which is 3 times 10 to the 5 pascals.